Thank you all for joining our webinar today on New Dimension of Polymer Analysis, timsTOF fleX workflows and capabilities. My name is Nancy Wright-Ross, and I will be your host. If you should have any technical difficulties during the presentation, please use your chat box and let me know. Also, be sure to download the handouts for this webinar, which are somewhat applicable to the topic. At the end of the presentation, we will have time for a brief question and answer session, and we ask that you use the question box located in the control panel in the upper right corner and direct them to me. If we are unable to get to your questions, we'll certainly be able to contact you offline. I would now like to introduce our presenter for this webinar, Dr. Artem Filipenko, National Applied Market Area Manager for Bruker Daltonics. Dr. Filipenko has been with Bruker for over 10 years and has over 15 years of industry experience in development of innovative methods and instrumentation for various analytical applications, including industrial, environmental, food safety, and homeland security. His area of professional expertise ranges from gamma spectrometry and neutron detection to ion mobility and mass spectrometry. I will now hand over this presentation to Dr. Filipenko.
Thank you, Nancy. Hello, everybody, and thank you for joining us for this webinar. The topic of today's presentation is New Dimension of Polymer Analysis with timsTOF fleX workflows and new capabilities. Today, we will be talking a lot about ion mobility, or more specifically about trapped ion mobility, and its applications in polymer analysis. So to begin with, let's review the fundamentals and make sure that we're all on the same page. So here we see two isomeric compounds, meaning that these molecules have the same nominal mass with different molecular formulas. Because of the same nominal mass, these compounds may be indistinguishable for nominal mass resolution mass specs, such as quadruples, for example. High-resolution instruments, such as time-of-flight mass specs, may be able to tell them apart by the small differences in molecular weight and isotopic patterns. But what will happen if two compounds have the same molecular formula, same exact mass, and differ just in their molecular structures? High-resolution mass specs may not be able to help us there, and we may have to look for another way to separate them. Fortunately, different molecular structures typically mean different collisional cross-sections. Simply put, collisional cross-section is the size of a molecule and measures how often it will collide with other molecules around it. Just like with these two sailing ships on the right of the screen, more sails or greater collisional cross-section means stronger interaction with the wind or a gas flow. Under the same conditions, we would expect a ship with more sails to move faster than a ship with less sails. And I know that in boating worlds, there are things like hull speed, but let's not go there right now. So same with ions. The larger ion with greater collisional cross-section will interact more strongly with the gas around and resulting in different mobility. So basically, with ion mobility, we separate ions based on their shape and size. Better yet, we can actually measure their collisional cross-sections, but we will talk more about it later. So ion mobility seems to be very useful. We can separate different ions and even isomers based on their size and shape, but why is it not a standard part of every mass spec system by now? Well, one answer is right in front of you. This is an experimental linear IMS QTOF system built by our collaborator in University of California in Santa Barbara. And for experimental setup, it works very well and provides ion mobility resolution of about 100. However, its ion mobility drift tube is 2 meters long. It loses ions along the way, and the duty cycle of the system is pretty low as well. Ions are introduced in batches, and the previous batch must go through the drift tube from the ion source to the mass spectrometer, so basically, in this case, from right to left, before the next batch of ions can be introduced. Obviously, these factors reduce sensitivity of the system, and the sheer size makes it less than practical for most labs. Great experimental setup, but not exactly a workhorse instrument for most polymer labs. So this is not what we'll be talking about today. Instead, we'll be talking about this. And this is quadruple time-of-flight mass spectrometer with trapped ion mobility separation stage, also known as Bruker TIMsTOF. Ion mobility as a separation technique has a very long history that you can track on the time scale on the right-hand side. It's more than 100 years. Bruker patented its timsTOF technology in 2011, and the first commercial instrument was released in 2016. What makes the TIMS different from everything that came before it is really three things. Firstly, it's a much higher ion mobility resolution of up to 200. With other commercial systems, you typically get a resolution between 40 to 60, and the resolution really makes significant difference for polymer analysis, as we will see in a future slides. Secondly, the ability to measure collisional cross-sections of the ions very accurately and repeatedly, and we will also see how that impacts the analysis. And lastly, it's the fact that adding this separation stage does not reduce the sensitivity of the system, but in many cases actually improves it. So let's take a look on how it works. This is a diagram of TIMS cell and electric field distribution inside of it. Ions introduced through a capillary, separated from neutrals, and pushed into the analyzer section through the entrance funnel. In the analyzer section, a neutral gas flow and an electric field counteract each other, while the gas flow pushes the ions forward in accordance to their size and shape. The electric field holds ions back based on their mass to charge ratio. So the ions basically accumulate and separate in an analyzer section in the middle. This first step of analysis cycle is called accumulation, and it looks something like this. As you can see, the ions face the gradient of opposing electric fields and separate according to their mobilities. Basically, each type of ion stops at the equilibrium point, where the push from the gas flow equals the opposite push from the electric field. The next step of the analysis process is evolution. The gradient of the opposing electric field is reduced step by step, and trapped ions are injected into the mass spectrometer for further analysis, something like this. Ions with greater collisional cross-section are eluted first, and the most compact, smallest ions last. This gives us an ion mobilogram spectrum that you can see on the right-hand side, also called mobilogram, which is not to be confused with chromatogram. These are two very different things. So that was the basic principle of TIMS separation. However, the actual instruments have one additional section in the TIMS cell to achieve much higher efficiency. As you see on this diagram, there are two sections with electric field gradients. While separation and elution takes place in a second section on the right, all incoming ions are accumulated and enriched in the middle section. Once separation and elution of the previous cycle is complete, all accumulated ions are transferred from the middle section to the analyzer on the right, and the process repeats itself. So this conveyor belt approach with parallel accumulation and separation allows us to achieve almost 100% duty cycle and operate with almost no ion losses. It means that by adding ion mobility separation, this system does not sacrifice sensitivity, but actually gains some through ion enrichment. This principle of operation is really what makes the TIM technology superior to any alternatives on the market today. And this is what the ion optics of timsTOF instrument looks on the inside. As I already mentioned, timsTOF is a quadrupole time-of-flight system with trapped ion mobility separation stage, and that's basically what you see here. The time-of-flight path on the right-hand side is not fully shown. It extends upwards above the slide. It's a V reflection configuration with thermal stabilization jacket, which means excellent mass accuracy and mass resolution of 60,000. The quadruple filter and the collision cell for MSMS experiments are optimized for work in unison with timsTOF. And the timsTOF itself is what you see on the left. The cell is only a couple of inches long, but provides the ion mobility resolution of up to 200, in contrast to that 2 meters long tube that we showed on the previous slide. A very important detail is the orientation of the inlet capillary that you can see on the left. It is installed on the right angle to the ion optics axis, which means that the neutrals and contaminants are not blown directly into the instrument, but evacuated right after ions are extracted. This design makes the instrument very resistant to contamination. And of course, this is particularly important when it comes to analyzing sticky polymers. Now we made it to the topic of the ion sources. The first models of the timsTOF platform were designed for use with electrospray ionization and HPLC on the front end, just like you can see on the left picture here. Most Bruker ion sources are easily interchangeable, and there are many different variations for different applications. For instance, we can swap the ESI source with APCI source and run the system with GC on the front end. And that, of course, provides a lot of flexibility already, but that's not all. In 2019, Bruker has introduced a new version of this platform called timsTOF fleX, and you can see it on the right-hand side. It looks very similar, really, but there is serious difference. timsTOF fleX brings MALDI capabilities, including surface imaging, by the way, in addition to conventional LC, ESI, and GC-APCI. So no longer you need separate instruments for LC, GC, and MALDI workflows. This multi-tool can basically do it all. The timsTOF fleX integrates the latest generation of Bruker MALDI laser technology. It's the same smart beam 3D laser found in Bruker high-end RapidFlex multi-top instruments. It provides maximum laser frequency of 10 kilohertz, which equals to about 15 pixels per second of acquisition speed in imaging experiments, and the spatial resolution of 20 microns, with an option to go down to 10 microns in so-called zoom mode. Basically, it's a perfect solution for surface imaging. And a dual ion source geometry that combines MALDI and ESI is the same one found on Bruker SciMax FTMS instruments. So it's very well-proven technology that really gives it significant edge. In a quick summary, timsTOF provides the highest ion mobility resolution of up to 200. It makes a lot of difference when it comes to separation of isomers or analysis of complex polymer mixtures, and we will see it in the following slides. It measures collisional cross-sections of the ions with high accuracy and reproducibility. It means that collisional cross-section values can be used as an identification criteria for analyze, just like accurate mass or retention time have always been. The duty cycle of the timsTOF system is nearly 100%. It means that sensitivity of the instrument is not reduced by adding this additional separation dimension, but can be increased through ion enrichment and better signal-to-noise ratio. So now let's review some examples of timsTOF applications in relation to polymer analysis. Heat maps like this one are a common way to present the timsTOF data. On the horizontal axis, we have mass-to-charge ratio. On the vertical axis, we have the ion mobility. Note, by the way, that we often use terms ion mobility and collisional cross-section almost interchangeably, since these two, of course, are codependent. Color gradient represents the ion intensity. And in this particular case, we're looking at polypropylene glycol, PPG, with average molecular weight of 2000. Generally, higher mass molecules tend to be larger in size and have greater collisional cross-sections. And typically it results in distributions like one you see here. Different branches on heat map may indicate presence of different polymers in the same mixture. Different structures such as linear branched or cyclical, or different charge states of the same polymer. And in this particular case, two main branches represent single and double charge state of the same polymer. So let's keep PPG 2000 and add a couple of other polymers for comparison. In particular, we have polyethylene glycol, PEG, and the copolymer EOPO. All these have similar average molecular weight between 1900 and 2000 Daltons, show two different charge states, and generally similar patterns. So let's choose a mass, say 1500 Daltons, right here, and extract what we call immobilograms for each one of these polymers. Extracted immobilograms, or EOMs, are similar to extracted ion chromatograms, but with immobility instead of retention time. So we can see the difference in mobility between the two homopolymers, PEG and PPG. And EOPO copolymer shows two extremums on its immobilogram. This makes sense because the polymer chain is no longer homogeneous, and multiple different sequences with the same number of the two repeating units may exist. This is simple enough, but what will happen if we had all three of these polymers in one mixture? Let's take a look. Oh, this is what it would look like, and there is quite a lot going on. Fortunately, using the software user interface, we can outline specific regions that we want to examine one by one, like so. If we do that, this is what we can get. The red region contains only PPG, and we can see its mass spectrum very clearly. The purple region contains only PEG. It looks a little cut in a lower mass range. I would probably extend the selection region to the left, but I'm not the one doing the experiment. In the green region, we have the EOPO copolymer, and the blue mass spectrum on the bottom is what you would get without TIMS separation. So if you compare these four, well, let's just say that it would be much more difficult to analyze the full mass spectrum. If you're working on deformulations or reverse engineering, this is an extremely powerful tool. It allows to deconvolute mixtures, find additives, and identify differences between samples, even at very low concentrations. Let's take a look at another example. Here we have heat maps of 4 different polymers in the same mass range. 2 heat maps on top represent homopolymers of PMMA and PBZMA, that's polybenzyl methacrylate. We can see the different charge states, 2 different branches. 2 heat maps on the bottom show copolymers with the same repeating units of PMMA and PBZMA. One on the bottom left is the random copolymer, and one on the bottom right is the block copolymer. Although the average molecular weights and other parameters may be very similar, from these heat maps, it's immediately obvious that these really are different polymers. This type of analysis can be used for quality control applications, almost like thin layer chromatography or TLC. Specialized software can compare these heat maps statistically to identify acceptable and unacceptable patterns. If we will extract immobilograms for the same 4 polymers around the same mass of, say, 2 kilodaltons, we will get pictures like this. As expected, 2 homopolymers show single peaks in their respective mobilograms and have different mobilities. Mobilograms on the bottom show 2 peaks each, which makes sense for copolymers. These peaks overlap and have different distances between maximums, reflecting differences in molecular structures those specific copolymers. Here's another similar example. The difference in this case is that this sample was analyzed using timsTOF fleX MALDI source instead of the ESI. One of the MALDI advantages is that it yields only ions with a single charge, producing fewer branches in the heat maps. Not to mention that without LC, it also generates results much faster and can be used for insoluble polymers as well. Again, we can see complete mass spectrum on the bottom left, which looks pretty complex. We can outline two regions of interest in the heat map and extract mass spectra for each one of them individually. Naturally, it makes it much easier to distinguish monoisotopic peaks. Here's an example of two polymetric relate polymers with the same MMA repeating unit, but different structures. One on the left is a linear, and one on the right is hyperbranched. We can immediately see the difference in the heat map patterns. If we extract and compare ion milligrams for both polymers around, say, 2,500 Daltons, we will also notice difference. As you would expect, perspective milligrams of these two configurations are different. What is interesting, though, is that the resolution of the linear polymer ion mobility peak is lower than for the hyperbranched polymer. It may indicate that rotation and vibration has greater effect on mobility of the linear polymer than for hyperbranched configuration. One of our customers, Professor Yamago of Kyoto University in Japan, has recently published a very interesting paper where he shows how the timsTOF technology can be used for synthesis quality control of highly branched polymetric relates, also known as PMMAs. And on this heat map, the doubly charged ions are highlighted by white circles. Hopefully you can see them there. And the sequences having the same number of MMA repeating units between 19 and 22 are connected by lines of different colors. So we have red, green, blue, and purple. The sequences having the same number of branching units between 1 and 3 are connected by white lines, almost horizontal. Solid, dashed, and kind of dotted, respectively. This plot allows to estimate the effect of the branching structures on the ion mobility. As it turns out, the ion mobility of ionized polymers increases with increase in branching number. From this heat map, we can extract a lot of information on the structure of and composition of the polymer, as well as its distributions. And of course, this provides a very powerful tool, not only for research and development of synthesis processes, but also for quality control applications and reverse engineering. For instance, we can select a region of the heat map and extract a mass spectrum, just like we did before. This will allow us to calculate the average molecular weight and its distribution for the given polymer series. And obviously, we can also do the usual N-group analysis. Specialized software packages can do that automatically. Or we can focus on polymer ions with specific number of MMA repeating and branching units and extract milligrams for each one of them individually. For instance, here we have milligrams for 19 repeating units on the left with 1, 2, and 3 branching units. So those are 3 separate peaks that you see in milligrams. And milligrams for 22 repeating units on the right with the same number of branching units. So again, 1, 2, and 3. It really is a very powerful method of separation and analysis in many different applications. Now let's switch gears and talk about software for non-targeted analysis. More specifically about Bruker Metaboscape software package. It can automatically identify and annotate unknown compounds and perform sophisticated statistical analysis with multiple samples. In this example, we're looking at results of PET oligomer analysis using timsTOF Pro and Metaboscape software. Oligomer components were extracted from 3 types of PET resins used in plastic bottles. So the software automatically identified and annotated all linear and cyclical oligomers, and even picked up some residue of an antimony catalyst. It's not exactly what you would like to have in your water bottle. Here's an interesting detail. If you take a closer look at the annotation list that Metaboscape generated, we can notice that 2 oligomers have the same molecular weight, retention time, and molecular formula. So these 2 are obviously isomers. However, the software also captures collisional cross-section values, and we can see that they are noticeably different. If we extract an ion chromatogram for this molecular mass, we will see only 1 peak. So these isomers collude, and without TIMS separation, it would be not possible really to tell them apart. However, if we extract an ion mobilogram for the same mass, we will find 2 distinctly different peaks. So now that we have separated these 2 isomers based on their collisional cross-section values, we can proceed with some SMS analysis to identify their structures. We can see that fragmentation patterns for these 2 are different. And based on analysis of the fragments, we can conclude that the first oligomer has a linear structure and the second one is most likely cyclical. Let's take a look at another example. In this case, we're comparing 2 different samples of ABS resin, sample A and sample B. Some differences are very apparent from these chromatograms. These are different additives. However, there's a lot more to these samples than what meets the eye. If we run the samples through the Metaboscape software, the number of differences would turn out to be quite a bit greater than what was apparent from the chromatograms alone. Once again, note that elemental compositions, elucidations, and adductines are annotated by the software automatically. So-called volcano plot helps to understand how the software determines both common and unique compounds to each sample. Each dot on the scatter plot represents a compound. Its position over X and Y axis shows its fold change and significance respectively. Basically speaking, further away a dot is from the center of the plot, the more specific that compound is to one sample or another. If we select one of these compounds on the volcano plot, we can get a box plot that shows comparison of intensities of the respective ion in sample A and sample B. And in this particular case, we can see that difference is quite significant. The list of compounds specific to sample A is formed using this very principle. Naturally, this method is a lot more accurate than simple comparison of chromatograms. For instance, these 2 emulsifiers are a difference that could not be identified from conventional MS workflow. But how exactly do we know that these 2 compounds are emulsifiers? Well, having just molecular formulas in annotation may not be enough, right? So we want to know what these compounds actually are and what is their function on the particular material. And Metaboscape provides a workflow to answer these sort of questions very well. We can select any of the annotated compounds from the list and use a tool called the compound crawler. This tool automatically goes online to open source databases such as ChemSpider and PubChem and comes back with the list of known structural candidates for each molecular formula. More often than not, there will be more than one structural candidate. In the given case, there are 4. The next step to narrow down this list is in silico fragmentation. The tool used for in silico fragmentation is called MedFrag, and it is also fully integrated with the Metaboscape software. This software tool performs virtual fragmentation of the candidate molecular structure, generating a list of extracted and expected fragments for each one of them. MedFrag then looks for these theoretical fragments in the actual experimental MSMS data and highlights areas of the molecule where this data agrees. Then, based on the number of predicted and actually found fragments, the most likely molecular structure is selected. Going back to the example of 2 ABS resins, now comparison of diachromatogram can be more meaningful. For instance, we can say that sample B contains coloring and cross-linking agents not found in sample A, and a lot more antistatic. On the other hand, sample A contains antioxidant not found in sample B. Again, if we're working on deformulations or reverse engineering, this is an extremely powerful approach. Same goes for identification of unknown contaminants, synthesis byproducts, or any other problems of this nature. And speaking of the coloring agents, did I mention that timsTOF fleX can be used for surface imaging as well? Now, as already discussed, timsTOF fleX has both ESI and MALDI sources on board, and we just have to mention some of the more interesting applications. Here's an example of a Bruker logo printed with black and blue inks and imaged directly from the surface. No matrix was used for this MALDI experiment. Some analytes can be lifted by MALDI without it. So basically no sample prep. We just tape the image to a MALDI plate, as you can see on the top left, and put it into the instrument. What we get out is spatial distribution of certain ion types that come from the surface, and specifically from the coloring dyes. For instance, in the middle on top, you can see the superposition of distributions for ions with masses 313 Daltons and 575 Daltons. We can look at them one by one, of course, as you can see on the bottom. And of course, for each pixel in these pictures, we can get a full high-resolution mass spectra. In this case, the pitch between the pixels was 50 microns, but it can be made smaller. So dyeing with mass 575 Daltons that you can see in the spectrum on the right turns out to be a common blue copper-based pigment used specifically in this dye. And of course, this workflow is particularly useful for analysis of surface material degradation or any kind of discolorations. And that brings us to the end of this brief presentation. Thank you very much for your attention. I will point out that timsTOF is one of many great mass spectrometers manufactured by Bruker, and you can see it here in the middle in its nice family of high-performance instruments. And at this point, I will take any of your questions.
Great, thank you. Really excellent presentation, Dr. Filipenko. We do have a couple that have come in, so I'll get started with those. The first question, are there any issues with base charge effects in the accumulation stage of the TIMS cell?
So I would say no if the method is set up correctly. So given that it's space-confined device, yes, there are limitations. You cannot have too many ions at the same time at the same place. You will run in some kind of column repulsion naturally. But for any practical applications and collecting data, performing measuring experiments, no, as long as the method is set up accurately.
Okay, another question. How long does it take to switch between the ESI and the MALDI ionization modes? And what other types of ionization can be used with the timsTOF fleX?
So switching between the ESI and MALDI source really doesn't take any time. So you don't need to reconfigure anything. You don't need to plug or unplug anything. So switch happens through a click of a button in the software. And actually, two ion sources can even be run concurrently. So for instance, you can run an imaging experiment with MALDI and use an ESI with direct injection for log mass calibration or something of that sort. Some people even experiment with tricky ion chemistry inside the source, but that's more esoteric. In terms of different ion sources, well, actually, as I mentioned, on the ESI side, those ion sources are interchangeable, and actually they're very easy to replace with different ones. And we have quite a portfolio, including atmospheric pressure chemical ionization, atmospheric pressure photoionization, atmospheric pressure laser ionization. There is also captive spray and nanobooster, as well as DIP direct probe, and even adapters for dark ionization. So there are many different options.
Right, next question. How does the ion mobility resolution affect instruments' ability to separate different analyses? And is there any easy way to estimate it?
Actually, that's a very interesting question. I'll have to go back to one of the slides that were good. This one. So this is the case where we're looking at two colluting isomers, as you may recall. And if you will look on collisional cross-sections here, measured in square angstroms, of course, right? You will notice the difference between these two is somewhere around 9 square angstroms. And it gives a resolution between the peaks that they pretty clearly stand apart, right? And that's not even the highest resolution mode. So it can do better than that. So to give you kind of rule of thumb, this system can typically separate peaks as long as collisional cross-section of the respective ions is greater than a couple of square angstroms. You will see the difference between them. And to give you kind of frame of reference of what square angstrom is, the length of the singular carbon-carbon bond is 1.5 angstrom. Double carbon-carbon bond is shorter, so that's about 1.3 angstrom. And the triple bond is shorter yet, that's about 1.2. So basically, when you look at these numbers, you realize that we're literally measuring the molecule down to individual atomic bombs. So yeah, that's very significant.
Great, another question. What is the mass range of the timsTOF fleX for polymer analysis?
So the mass range of the instrument is from 20 to 40,000 Dalton. The instrument in its core is a QTOF, right? So there is a quadruple in it. And quadruple is really a limiting factor. But 40,000 is typically more than enough for most typical applications.
Okay, another question. How does the addition of the trapped ion mobility stage affect sensitivity of the instrument to low concentration additives and contaminants?
Actually, I think we discussed this question extensively through the presentation, but maybe let's go back to one of the examples. So here, for example, right? So we have complete mass spectrum on the bottom, which looks pretty complex. And imagine that you have some kind of additive sitting inside that spectrum. Needless to say, it would be quite difficult to fish it out and perform any kind of quantitation experiment, for example. So on the heat maps, like the one you see above, any kind of strong present additives will typically show up as pretty bright dots. But even if they're not present in very high concentrations, right? Just by selecting specific regions and illuminating all the background, like we did here for PPG, for instance, right? We win a lot on signal-to-noise ratio, which means that sensitivity on the instrument becomes much higher. And that, in addition, to pre-concentration effect that I discussed earlier when we do parallel accumulation and elution separation in a TIM cell. And of course, we do not lose any ions doing so. So basically, it's a combination of better signal-to-noise ratio and pre-concentration in a TIM cell.
Okay, here's a question. Is there a limit to the mobility range? All the plots seem to only go to about 1.7. Well,
there is a limit to everything in life. I do not recall exact number from the top of my head, so maybe let me get back to you on that.
Okay, no problem. Can pyrolysis be used with timsTOF for polymer analysis?
Yes, absolutely. So as I mentioned, there are many different time sources that can be used interchangeably with this system, including APCI. And in particular, there is very nifty adapter for GC-APCI applications. And that works very well with pyrolysis systems on the front end. In matter of fact, just recently we released a new application note describing a very similar application without TIMS, but with a QTOF instrument. Works very well.
Great. Well, we're out of time right now, and I want to thank everyone for joining us this afternoon. You will receive the recording of this webinar within 24 hours. Please also be sure to visit our website as we continue to add to the virtual webinar series at www.bruker.com, and please stay safe from COVID-19 and have a great rest of the afternoon. Thank you, everyone.